So it is what I saw on my side. Is only Japan who.
Yes, in my video, I didn't mark from 12 p.m. to 1 p.m.
I think all funds
Shifted?
Yeah. I think for me, I said for Thursday, I didn't mark 11 to 12.
So maybe I will do this slide.
Maybe.
Oh, you have it printed, right? Someone.
I have it. Yeah.
Maybe we take this first page and let it go around, and everyone marks once again by hand, because it is a.
Yeah.
I do not want to make anyone uncomfortable. We have a backup solution of recording and watching it online, but having everyone or maximum amount of people here would be the best thing. So please, let's put a little star here and put it around so I read only one cut.
Oh, just on this one.
So when we were meeting for the first time, we looked over the textbooks and the plan of the class. You might have seen the recordings. And right now we are on the chapter for molecular models, and we need to get over molecular Hamiltonian concept. So this is what we were doing in the lab last night. So for using molecular models and sending them for computation from the cluster when it's Linux, some command line, and there are several commands that are helpful. The most complicated is escape moving for YouTube. So it is and here is a list of skills that probably will be accumulated in everyone by the end of the class. Some of you already have partial skills and you will improve and master. And you were doing collective approach by coming to the board and writing this. So by creating models and implementing theory for both software and hardware and find properties of materials. So it can be used in science and engineering or designing better materials for applications. And ideally, predictions should coincide with experiments, measure correctly success. So then we discussed the language of what is molecule, right? So which is like collection of positively charged nuclei and negatively charged electrons. And we spent substantial time without any slides and recordings by discussing with the following thing. If we do have a model of material, a set of atomic coordinates for ions, coordinates for electrons, what is the next step? Which is to formulate a Hamiltonian. And if one has a Hamiltonian, one can go to molecular dynamics or to show the equation. So the Hamiltonian is, you are telling, you are teaching us an operator of energy, which can be kinetic, thermal, and potential. Okay? And one needs to do it on the mathematical level, mathematical language. Okay? As an input, we have positions and velocity, so momentum of each particle. And as the output of our little intermediate step, we do have the energy. Nuclei, electrons, we get Hamiltonian. So what we are going to do can be split on in parts. First part which is not very creative, but one needs to be careful about it, is to set up mathematical symbols for all these positions and momentum, so that one can use them in the equations. And second part is, maybe it's a background before we go to the details, is to remember what are the equations for potential energy between charged particles and what is the kinetic energy of the moving particle. So let's practice it. So the potential and kinetic energy. So if we have a particle of charge Z1, the charge Z2, they are set up on a distance r. What is the energy of potential energy between these particles? Coulomb's law. Can you dictate me approximately what it is? Anyone wants to help either write it down here or just suggest what is Coulomb's
law? The attraction between two charged particles.
Good.
And correct. And the vice versa of their distance, square of their distance.
Excellent. Product in distance. Product of charges, right? You got this idea? Yeah. Can you help us writing it down? Yep. Use finger. Just write down your vision of.
It's over the distance, or the distance is square.
Force is distance square, but energy is over the distance.
Over the distance.
Over the distance?
Yep. It should be a constant, but okay, yeah. Thank you. Yeah, that makes sense. So potential energy, we can call it U of R equals constant, right? And then one gets interesting observation. If both charges have the same sign, the energy is positive. If both are negative, energy is also positive. But if one is plus another is minus, it is negative. So negative energy means stabilization. They want to come closer to each other. Positive energy is there, repelling. And 1 over R means when they are close, the energy, absolute value of energy is huge. Thank you much. Is huge, and when they're far enough, one can neglect. It becomes zero. So you got the Coulomb's law. What about kinetic energy? If we have one particle which has momentum P1, or if you do not write momentum, it has mass. M1 and velocity 1. What is the kinetic energy of motion?
P squared by 2n.
Perfect. You do not need this course, you can teach it. P squared over 2n. So we are ready to write the molecular Hamiltonian. We have all background. So we will carefully set up variables for all positions and all velocities, or all momentum of charged particles in the molecule. And then for each particle, we will set up kinetic energy, and for each pair of particles, we will set up potential energy. And then we will add them all together. if it is like one hydrogen atom with one proton and one electron, there will be two terms for kinetic and one for potential. It will be rather short. If you will have more and more atoms, it will be like many lines. But we need to recognize this because it is like a background point from which any computational modeling of molecules and materials is done. So we set up potential energy, we set up kinetic energy, add them together and form total energy of Hamiltonian. And then if we want to do molecular dynamics, we just practice second Newton's law, this derivative over position to get force. Or if you want quantum properties, we plug in this Hamiltonian into Schrödinger equation. Right? Last year someone was writing it, but I have no doubts who saw it. Hamiltonian acts on a known wave function, gives eigenenergy and unknown wave function. If the equation is solved correctly, this wave function takes shapes of clouds. It's a major equation of this fundamental quantity. Another point of my curiosity to you, which brands, which types of Schrödinger equation can you see? Is it only one Schrödinger equation or at least two? If we, and everything is there. If you recognize equations and their difference, you can just name them. It's not a big intrigue. I'm not hiding it as a complicated question. Like, what is the difference between first equation and second equation?
First one for one-dimensional and the second one for n-dimensional.
Good try. But there is a little bit more in that. So, when we were speaking about Hamiltonian, we were including their only positions and velocities of nucleus. There was no time. And so, by the way, if we set up kinetic energy, P square over 2m, one of the important main basic equation, if you take a course in quantum theory, which you have taken before and you may refresh your knowledge, maybe you're probably required, maybe not, but there is a, I'll give you quantum theory in 2 minutes. A refresher. So instead of particle with a specific coordinate, a quantum object like electron is wave function distributed. But one still can speak about momentum of this particle, although it is distributed everywhere. So in order to get momentum, one needs to take a wave function, it is one dimension in the x, and apply derivative over position. Derivative over position. And put minus I h bar. So this will be momentum derivative. And if one is formulating kinetic energy in quantum theory, one replaces single peak momentum with this derivative over position. Momentum square will be derivative square. Right?
Can you repeat it again? Can you repeat it again?
Absolutely, absolutely. It's my favorite subject. Let me see if there are empty slides. Okay. I will be speaking and writing. Maybe it will be better for you. So, there is a classical science, physics, chemistry, and there is a quantum theory. in classical, we have just momentum as a number. In quantum, we have momentum as expectation value, which rests on the constant wave function. Will give the expectation value of momentum. So there is a distributed wave function, and out of wave function one can extract expectation value of an observable, for example, momentum. And in order to do this operation correctly, one needs to set up a little rule, a way which differential operator is placed here. And the major part, the cornerstone of quantum theory force and general theory for this momentum, we use minus I, constant, to details. So everywhere where one observes momentum in classical equation, like for kinetic energy, one needs to place this differential operator. And do not worry, this is not theoretical course. We are not going to derive tons of equations. We just need to see background and superficially observe connections in the past. I will give very little homework that can be done in 5 minutes, but it will be easier than it's on the level of kindergarten. That you do not worry. I'll explain it as we go. It will be mostly about drawing circles and connecting them very lines. But you can ask your junior family member to do instead. Okay. Oh, yeah, we need to get over all these two equations. So, when you do molecular mechanics, molecular dynamics, what is the goal of such simulation? Not the industrial goal, but technical objective that you want to pursue.
Simulate a bunch of the atoms and define interaction and forces between them.
But if it is dynamics,
their
behavior, how their positions change in time, trajectory, right? That you can visualize by moving.
Or is the molecule at that specific time?
Ah, what is the molecule? Yes.
Position.
Yes. Position is function of time,
yeah,
which is called trajectory. But if our objects are quantum objects instead of classical, so if instead of positions of atoms and positions of electrons, there are wave functions, what is the analogy of molecular dynamics on a quantum language? If on classical language you have just particles moving, trajectories, but if each particle is a distributed cloud, we need to see how these clouds change in time. And major primary Schrödinger equation, or otherwise called time-dependent Schrödinger equation, answers this question. It shows how the wave function changes in time. So in your Newton's equation, you have second derivative of position. In Schrödinger equation, you have second derivative of wave function that depends on several things. It's not only that; it will be more dimensions. So this time-dependent cloud distribution, and it changes forward in time. And it is originally it is correct Schrödinger equation, but it is already mixed type. And there is a trick to simplify time-dependent Schrödinger equation into time independent Schrödinger equation. So the little mathematical trick, it's just 10 seconds to tell, but I do not want to overwhelm this. quick mathematical trick reads of removes the dependence on time and makes it time independent. And for time dependent, there is a dynamics of this cloud, how it changes in time. In time independent, those are eigenstates. So it is not n-dimensional, it is number n, it is index of solution. So for eigenstate problems, like in linear algebra, when we find eigenvalues of matrices, we have multiple solutions. So this is index of solution, eigenvalue problem. Good. Does it put anything from your previous slide? Another process? A little bit?
So in the quantum chemistry, we use the wave function to represent the position in the molecular dynamics.
I've got your question. I want to reformulate. You're asking what is the technical goal of the computational chemistry area of activity, and you expect that the goal is to find trajectories, right? Atoms.
Atom moves.
Yes, but it's not the whole story. There is another goal which is of equal importance, and some people consider this even more important: to find energies of eigenstates. So if one is looking for electronic properties like conductivity, or if one is looking on the optical properties like ability of a material to absorb a weak light, or one looks onto ability to oxidize and reduce like more chemical. These energies of that can be found for each molecule are critically important. And in broader sense, computational chemistry is to find trajectories of atoms, as we covered this week, plus finding energies of eigenstates. So this energies of electronic states is critically important part. We are pursuing this goal as well. Make sense? There is also a little trick that we do not need right now, but it makes a connection between those. Maybe some of your viewers will have reached to just pronounce it. If you know the solution of time independent, you can construct solution of time dependent by adding them together and multiplying each of them by imaginary exponential. So solution of time dependent is a superposition of time independence. It's, if you are or will take differential equations, it is, of course, it is quite standard procedure. Compose, find connection between general and particular solutions. But right now, do not overload the way. If you need, I will repeat. There are more important things. This is not a major part. And this is the same idea I just copy pasted either from the textbook or from one of my colleagues' slides. Superposition of time-dependent solution. Okay, so most important part that we need to complete. I'm not going to overuse the time. Let's consider molecular hydrogen, H2 molecule. Two products and two electrons. And set up a Hamiltonian. We're not going to solve it. We're not going to find any eigenstates or trajectory. We just need to rigorously write down a Hamiltonian. And do not be discouraged. We will do this little exercises, and later on, when we will run software, it will be very auxiliary concepts like fundamental. So you already visited the port. Can I ask you a question to help me drawing something? So please draw 4 circles. 2 circles with plus inside and 2 circles with minus inside. Yeah, thank you. Sufficient. I told you it would be easy. It will be like, your homework will be like this. So this is proton, another proton. This is first electron, this is second electron, right?
For CH1.
No, I was intending press. Let's keep it. So mathematically, if you want to specify position of those, we need to select an origin, a system of coordinates. So select a point somewhere. Yeah, and just put letter O for origin. O. And now please connect origin by arrows to each of the circles. Escape. Can I do this? Yeah. Yes. Yes. And last one. Good. Thank you.
Thank you.
So those are positions of ions and nuclei. So let me write down things. So for electrons, there is a small mass. For nuclei, there is a big mass. The charge is the same, like elementary charge. And position, we can call it, for electrons, it will be R1 vector, R2 vector, lowercase. For nuclei, we may use uppercase, R1 and R2. Right? I'm going to change the color to red. Please. Mass? And it is my poor calligraphy. It's for letter M and the word mass. Good? Yeah. Okay. I like your drawing. I was preparing and made some pre-made drawings. So good picture. Okay. But you probably did better. So, position, right? Now, remember, if you want to practice Coulomb interaction, we do need distances, right? So distance between two charges, it will be another vector connecting the charged particles, connecting the particles of the same sign and connecting particles of different sign. Can you comment that? Just connecting particles by arrows. This will be, you can keep it just as a line. So that will be repulsive interaction between two classes. Then this will be attractive interaction between plus and minus. This will be also attractive interaction between plus and minus. This will be repulsive between minus and minus. This will be attractive. Escape. But you did it. I'll compliment. Yeah, thank you. Oh, it is here. And one more attractive. So from this little diagram, each line here corresponds to a term like 1 divided by R1 minus R1, right? With charges and constants. How many terms like this we will see here? 1, 2, 3, 4, 5, 6. So we will have already a long Hamiltonian. Repulsive, destructive, and more. So it will be not a big deal to write down the potential energy, right? For kinetic energy, we do need momentum. Electron, first electron, second electron, and momentum of first nuclei, second. And based on each momentum, it will be just one term. Okay? For kinetic energy, it will be if electron has momentum lowercase p1, p1 square over 2 mass electron. Then electron number 2 square 2m. Then p uppercase those electrons square over 2 mass nuclei plus uppercase p 2 over 2 mass. So this will be kinetic energy. So total 6 for potential and 4 for kinetic. And if one writes it down in a row, it will be molecular Hamiltonian, total operator of energy that one can use either towards molecular dynamics or towards eigenstate of Schrödinger equation for electronic states. Six terms. We are not going to rewrite it. It was already written. We just take pairwise nuclei 1 minus nuclei 2 positive sign. And later on we will introduce atomic system of coordinates where charge of electron is 1 and constant in front of Coulomb is also 1. It's a very comfortable system of units where one can skip this constant and we will have then repulsion of 2 electrons, lowercase plus. And then there are 4 terms where uppercase letter, lowercase letter, 1 minus. Upper, lower, 2, 1, minus. Upper, lower, 1, 2, minus. Upper, lower, 1, should be 2, 2, 1, 2 here, minus. Okay. And you know that if you have two positions of vectors, distance between their points will be vector subtraction, like in middle school or high school. Right? Adding subtracting vectors is adding or subtracting their points. So, in some sense, we are done, but I would like to go over this material once again and look on the same equation from different angles. Why? Because there are some standard notations. There is an attempt to compare apples to apples, and origins to origins. And although dimensionality of all of these terms are energy, you'll observe even for one of the smallest possible molecules, molecular hydrogen, there are 10 terms in the Hamiltonian, which is a little too much for humans. And one should practice the principle of ancient Romans, divide and conquer, to separate them on groups and make special treatment for each group. So I suggest to split them onto 5 groups. If you split 10 objects into 5 groups, it probably will be easier to do it. So one, in this, there will be one group of two groups for kinetic terms, N for nucleus, E for electrons. And then there will be potential terms, N for interaction of nucleus to nucleus, E for interaction of electron to electron, and Ne nucleus to electron. Will you please try to help? And you may start from most challenging part, from the last row. The rest is so easy that it will be boring. So, potential energy between nucleus and electrons.
Constant term.
Suppose that all charges are 1. 1? 1? Divide by R, and then put index maybe 1 and 1. And sign will be negative because the atomic. Then next one, there will be total 4, right? Minus? Yeah. Huh? Okay. And there is no space for writing more. Thank you. Thank you. You already did a big contribution. So it is first electron attracts to first proton. Second electron attracts to second proton. But in addition, there will be second electron attracts to first proton, and first electron attracts to second proton. Crosswise terms. I didn't learn your names enough to pronounce them, but your names probably starts with Gwen. Can you please come and help? Which term would you like to?
Potential energy of electrons.
Okay.
So what am I from?
Potential energy of electrons, you write here, continue this, I think it's a good sign.
Okay.
So, yeah, electrons attract. So the sign will be plus. Plus, and there will be fraction. Yeah, on the nominator there will be 1. Up top, above. And in the denominator there will be subtraction of lowercase r1 minus lowercase r2. Try B. 1. Minus r2. Lowercase. Excellent, excellent. Thank you much. So, by the way, this is most challenging part for computations. This electron-electron interaction is responsible for many fine effects that changes properties. Let's go on the circle once again. So,
the potential energy of nucleus.
Okay, good. Yeah, excellent. Thank you. Good. Now you need to do this kinetic energy. And you have a freedom to select either electrons or nucleus.
Kinetic energy of
Okay.
so that was right, that was the fraction.
Yeah. In the denominator uppercase P.
Right, divided by
2 months. Uppercase N.
For articles.
Yeah, and maybe this one should have subscript 1 because first nucleus and put square. P1 squared.
or
Yeah, just. Yeah, and second one, the same, but if you repeat two squared. If it doesn't work, don't fight with it. It's the idea.
oh, sorry.
But we all understand what it is.
Okay, thank you.
They can do it as well. It gets not very cold. Okay. And the kinetic energy of electrons should be the same as kinetic energy of ions, but momentum should be lowercase, right? And mass should be lowercase. Excellent. Yeah, many thanks to everyone for cooperative effort. And by now, by adding together all these groups of terms, we have a molecular Hamiltonian. Right? When a computer code is running, such molecular Hamiltonian is being implied for each model that you're doing. It may not write you immediately these terms, but it is considered to exist, and all equations and numerical solutions are based on such formulation. We're doing from year to year, and sometimes, if it is 2 or 4 terms, it's not a big deal. You can write them all in a line. But if you have like 100 or million atoms, it's a little too long to write. But you still may want to discuss it. And then since a lot of terms are repeating and having the same nature, they differ only by index, one can use the symbol summation. So P uppercase with index I for ion, and I goes from 1 to 2 if it is molecular hydrogen. If it is million atoms, it is from 1 to million. If it is the same mass, you can keep it constant. But if you have different hydrogens, carbons, nitrogens, one can take into account that each ions have different masses. For electrons, summation from first to how many electrons we have. Momentum lowercase with index I, lowercase for electron, divided by 2m. For nuclear interaction, charge of nucleus number 1, nucleus number 2, and there is subtraction. And if there is more than one can put indices I and J and make summation over all groups. Same for electrons. When they are attracting and there are only 2 electrons, it's one term, R lowercase 1 minus R lowercase 2. But if there are more than that, one puts indices I, J, and makes summation. And if it is nuclei to electron interaction, you have upper level for position of nuclei, lowercase for position of electron. You run summation. I goes from 1 to 2. I lowercase go from 1 to 2. Minus because they attract. And you put charge of nuclei. In our case, we put on this charge number will be 1. But if you have a carbon nuclei or some charged particles, you can put different things. Ocean will be, and then this molecular Hamiltonian of 2 kinetic and 3 potential groups, kinetic nuclear, kinetic electronic, potential nuclear to nuclear, potential electron to electron, potential nuclear to electron, are plugged into time differential equation, and one solves for molecular wave function and total energy. We will discuss this equation again and again. This is a function of many variables. If you have 2 nucleus, it means each of them has 3 Cartesian projections. It is 6 independent variables for position of then we have two elements, 3 Cartesian x, y, and z for each. 6 independent variables for elements. Total 12. So it's a function of 12 variables. It's already an ugly function. And if you take bigger models, it will be more and more independent variables, which can be solved sometimes, but it's a waste of time. And I will not keep you into it, I will tell you this. The subject of computational chemistry is to develop tricks to reduce dimensionality of this wave function. Find what can be neglected. Because wave functions with too many independent variables are very hard to solve. So by now you know the main idea of the course. Okay, so to entertain you during the weekend, I would like to. I printed it at home but forgotten it, so I'll send it again by email. You'll see here. So please try to consider a cation of hydrogen, which means 1 electron less. So you may want to draw a schematic diagram, same as you did in class, connect arrows, label, put vectors, and then identify the ion to ion, electron to ion distance, and basically write molecular Hamiltonian. Since it is 1 electron less, you can just work on what we did in class and remove terms which are not needed. Right? That's quite doable. And since in class altogether we were doing it for like 40 minutes, at home for simpler systems we'll do it in 5 to 10 minutes with guarantee. Just try to just draw it on a piece of paper and bring it to class or scan it. Nuclear, electronic, potential terms. If you really want, if you have nothing to do, if you do not have entertainments on the weekend, you might try to do the same for lithium hydride, because lithium has charge 3 electrons, and hydrogen has 1, so it will be false on the 2 nuclei, but at 4 electrons. Okay, I think it is enough. So have a nice weekend. I'll review and send an email about this stuff. I can try doing it now, but I'm too excited about the class material and can do not focus. And, have a nice weekend. Looking forward to see you next week.
Thank you.
Prepare some results.